with this we have also the beta reduction, the braid reduction, which is something that is typical of this calculus, that is obtained by swapping T1 and T2. I gave also some rules. Maybe we can discuss later if with people who are interested. And what else? This is an important issue. Contrary to the lambda calculus, here we are talking about approximation. The computation here is an approximation process, so we can stop whenever we like. So the process can, the reduction can go on forever. I mean, because braiding is something that you can keep doing until you get the precision that you want to get. That's how it works. At that point, then you just measure it. Okay, but still, we can define. Well, this is an example from the paper that I tell you about. I told you before about the quantum, the topological quantum compiling. This braid represents the control knot gate that operates on 2 qubits. These are the encoding of the 2 qubits, the control qubit and the target. Okay, you need 3 anyons. With the Fibonacci anyons, you need 3 anyons for each. Okay, and then the braiding, this braiding, I mean, gives you the C knot. Okay, of course this can continue forever, and the longer the braid, the more precise the result. It is open, the question whether you can get a precise result at some point. I mean, that's not obvious and that's not normal. So you can just get result with some approximation that you can refine. That would be the C knot. Yeah, that's the pattern. And but even if the computation never, I mean, we can define a kind of normal form like in the lambda calculus. So essentially, the normal form is a term which does not contain any beta redox anymore. But this doesn't mean that the computation stops. You can still go on with the braiding until you reach the precision you like, and that's the difference with the classical lambda calculus. So that would be a computation. This is the final measurement, where you essentially do the inner product, which means essentially fusing back. This represents the fusion back of the anyons. We think we have proved confluence, but maybe we can discuss the details of this result with whom is interested. And here is just a very simple example of a term. I represent this as a tree, but this is a lambda, an anionic lambda term, in the sense that this is my tree, this is my term. This subterm is the variable, okay, and the subterm represent the control qubit, okay. So depending on the instantiation of this, the result would be the application of P, the phase gate. With this, I indicate the braiding that do the control, the phase, and then you have to do it back, because that's the computation, in order to get reversibility, of course. And so you would get different results here depending on the instantiation of this. So this is a function of the first qubit, and the reduction of our rewriting system applied to this gives the final result. I mean, I'm just giving you an idea, of course. All the details, there is a lot of details to be discussed, but if you want to ask me any, yeah, this would be the C and the P gate would look like braiding. And This is the encoding in the Fibonacci system. This would be the term encoding 0, and this would be the term encoding 1. Of course, you cannot draw exchange, it's just a number of the reference. And that's essentially all. If you want to ask any question, then the calculus of the telephone. Yeah.
Okay, so let's thank.
Okay. So I actually got the. Is it okay? Okay. I got a little bit lost at the point of onions, and the problem is that I don't understand. So it's a two-dimensional system, means it's a two-particle system.
The particle is two-dimensional. It lives in a plane.
So what would be one dimension?
No topology there.
Dimension in which space?
In a plane. So your particles move in a plane.
And so you actually fix their coordinate.
Yeah, you fix.
But then for coordinate, it doesn't commute with
You
space, so
fix
don't
a
know
surface. Okay. So it could be any.
in our Euclidean dimensional space, or I don't understand which space. In which space? So
Any two-dimensional space. Plane.
yeah, so, but physically, for example, okay.
Surface of a superconductor, for instance, would be
Okay,
a physical.
So that would be a two-dimensional subspace of our three-dimensional Euclidean space.
That would be a physical realization.
Is that?
Yeah.
So
But
basically,
it's
you have
on
a table.
Yeah.
On a
And-
table, you have many particles, and these particles are interacting with each other, and finally you reach some configuration. Then you stop. Then you measure. Then you get the result.
No, you're getting too fast for me. I don't understand. No, first of all, I want to understand. So, for example, a position of a particle, let's say electron, can be described.
You cannot talk about the electron.
Yeah,
Yeah.
you
It's
only
like,
care about topology.
it's a quantum particle. It's not. I mean, it's like a
It's not
phonon. A phonon, you know, a sound wave is actually quantized, so it behaves like a particle, even though it's actually an action over lots of physical particles. So an anyon is a quantum particle in that sense. It's
There is a position observable, position operator. Okay, it does not commute with the momentum operator. Okay, so position is multiplication by x. It's operator of multiplication by x, and then there is momentum is it's a Fourier transform. Effectively, it's a differentiation over x. These are two classical, but quantum non-commuting. It's a classical conjugate pair of non-commuting observables, right? Position momentum. So if you fix coordinate position, of course you don't. There's nothing.
I think you shouldn't.
Yeah,
Maybe you want to.
I think they're actually. I mean, they're quite coarse-grained, these things. I mean, it's not. You know, you wouldn't think about the physical area they subtend. It's a very abstract space in which they're moving. The key point is that it's two-dimensional, and therefore you've got these topological
So you
effects.
don't know
If
where
it were
they're
three-dimensional.
So we don't know where they're moving. So
You can only
what's
model.
the space?
Well, you know, so there's something happening in a physical space, but it's like, you know, imagine sound waves. If you've got 2 degrees of freedom, then you can hypothesize that there's a two-dimensional space.
Okay, so you're saying that there
but
are
it's not
2 degrees
necessarily.
of
It's not
freedom,
a.
okay. So let me put that question just a second. What are the observables? So when you talk about an onion, so what are the observables that I can observe experimentally? So for these electrons, for example, I
The
can
final phase that you saw. You do the braiding, okay, like. It's what's the definition? The observables are the results that you get here. The phases, the numbers.
Okay, so this would correspond to some kind of eigenvalues of some operators. So these are the observables are usually self-adjoint operators on the Hilbert space. So I just want to understand what is this operator and.
Is a trace invariant essentially what you calculate?
Yeah, well, let's say you're saying that there is a probability of observing this thing, yes? So the probability in that sense is a trace of an operator in that case, of a projector. So we take a projector on the subspace, and this probability would be a trace of let's say, of a projector on the Hilbert space. That's basic quantum mechanics. So I want to understand exactly what is the observable would be. So what I will observe in experiment.
A number.
Yeah.
A number which will be
You get
probability
the
of
number.
what? Probability of, let's say.
Is not a probability, is the calculation of the phase.
Okay, so there's a phase is an observable. Okay, that's a. By the way, okay, so for a spin, by the way, phase it's a continuous spectrum. It's already infinite dimensional space. So it's all rotation.
Yeah, you can get any complex number.
So I mean, the analogy of vortices is pretty good. I mean, you know, vortices.
Vortices.
So you imagine a vortex and an anti-vortex. You know, they could be quite physically large, but you know, have such little energy that they're quantized.
Mm.
So the ordinary sort of momentum operator and so on doesn't really factor into it.
Yeah, you can say the momentum is more than little less than it. You can convert it into binary. Yeah, so
Well, it's right. I mean, it's classical almost in that sense. You know, it's big enough physically to be classical in the momentum and the physical position space, but in terms of the energy in the vortices, it exhibits quantum behavior. It's quantized.
But your questions are too difficult for me because they are too physical.
But this is the basic. I think if we don't understand these basic questions, we
should
cannot
ask
move on.
something
I
about
don't
computational.
understand.
Give him one computational question.
Okay.
Because this is all just
How do
physics,
they
right?
ask
Mm.
Yeah. So I'm just wondering, is there kind of like quantitative aspect of your calculus? Because I mean, it seems that the whole like physical process is.
So the quantitative aspects is.
Yeah, this here you present this lambda calculus, and it seems that everything is I mean, either like deterministic or non-deterministic. You don't really. This calculus does not involve any, for example, probabilities or
No, that's
any.
not true.
Okay, so.
Because as I said, the calculus, differently from the lambda calculus, is an approximation. What you get is an approximated result.
Yeah, but how do you measure this approximation? And how do you, so if I understand correctly, so you have initial term, then this term can involve, can do this like term rewriting, or even in this case like tree rewriting.
Yeah?
You get another term, and so how do you get the quantitative measurement of this term?
I can show you. So differently from the calculus, you get these numbers here. So the quantities are there, and also you get this operator, okay, which is also giving you a number.
So you're looking for
at the
some probabilities somewhere.
I don't know. I mean,
amplitudes.
probably something. I mean, not necessarily probabilities.
But maybe
Yeah,
the
those are
alphas.
numbers.
The alphas are amplitudes, or
Yeah. They are complex numbers, okay. So when you do then this is the end of. So this means that you do braiding reduction, beta reductions, okay? Then in this braiding you compute something. There is a number here.
so the
Okay.
alphas will change when
Yeah,
you're
the
doing.
alpha will change.
Yeah, so
Okay.
those are the
And
amplitudes.
then
Okay.
when you measure, which is this inner product essentially that you do here,
Yeah.
the semantics
Okay.
will be then you compute a number.
Yeah.
Okay.
So there
Okay.
is actually some measurement, but this measurement is not part of your calculus.
The
Because it
measurement
doesn't really
comes
matter.
Yeah.
out from
Yeah.
the
Somehow you say at some point you
Yeah.
could measure, and that means like you're looking
Exactly.
at, then you're
The-
able to actually read the alphas.
Exactly. You're
Okay,
right.
so you have to
The measurement-
define the measurements. I mean, as a kind of like.
No, the measurement is the inner product, right? That she's doing at the end. Kind of.
Yeah.
but
It's not part of the calculus syntactically,
yeah.
but
Exactly.
I can give you in the I can
Yeah,
somehow just model it as a term,
Yeah.
okay, syntactically. But the semantic, the meaning of that, I mean, of course, I didn't define any semantics here. I have to tell you also, no, the notational domain and the correspondence and the type.
Yeah,
Of course. So that's the question. Your question is probably because I didn't give you any meaning of this. This is just the rewriting system, but.
Yeah, exactly. This is purely like syntactic term rewriting.
Exactly. The domain would be a Hilbert space, and therefore you get numbers there, and the result is modeled via the inner product in the Hilbert space.
Oh, okay. This goes back to like standard model of
Once you've got a
quantum
Hilbert
system.
space, yeah.
You still have a Hilbert space.
Yeah, and the nice thing is that the algebraic model for topological quantum computation, which is this is this modular tensor category, and there is a modular functor mapping this modular tensor category into a Hilbert space, which is something that is true in general for quantum field theories, where you have this mapping class group and the modular functors that gives you the Hilbert space, the vector space associated. So my semantics would be the Hilbert space.
Okay,
right?
that's great.
Yeah.
I mean,
But you could actually add that. I mean, you could have like a much more complex syntax. And
Yeah,
have
you could add
you could
add a
add into the
measurement
model, like,
operator.
and make it more complex, and then you really very
Yeah, yes.
It's probably
Yeah,
not the point, because it's a very classical way of doing this
Yeah.
Hilbert
Mhm.
Yeah,
space
if this-
operation.
But I think what you have is probably a subspace of the modular tensor category syntax. Yeah, or is it?
but why
A
does that
subspace.
matter?
Probably doesn't matter. Yeah.
No, what you mean is probably that I get something. So the modular tensor category would be an abstraction of this.
Right.
Yeah.
Sure.
Yeah, and also the Hilbert space, which is then out my denotational semantic,
Yeah.
an abstraction, but I think a kind of correctness result.
Yeah.
So I can map any term in an object in my Hilbert space.
But suppose you have finite types. Do you get finite Hilbert space?
Yeah, I work with. What do you mean finite types? This calculus is untyped. I didn't think of adding.
No,
types.
type. I mean this.
Type of anyons.
Yes.
Yeah.
And you suppose that initially you have like 3 particles. So initial you have just finite number of particles. Do you get a finite Hilbert space?
Yeah.
Okay.
But then you can always add particles and then get.
What do you mean?
So you can the system or the semantics of you can see as a direct sum of Hilbert spaces, because you can always in any moment create particles from the vacuum and also destroy particles.
There's a Fock space.
Yeah, this Fock space. But okay, suppose that I don't do that. Suppose that I restrict myself to just initially I have like 5 particles. I never introduce any new particles. Probably you can destroy some of them, but I don't want to introduce on the way. Just like you have initially, I have 5 processes. You don't want to create a new process, because that would make your life much more difficult. So we still live in a finite. And what's the dimension of this Hilbert space?
The dimension is given by the different ways in which you can get the intermediate results of the fusion.
Okay, so that complicates the formula somehow on the slide.
For the Fibonacci anyons, it's very simple. If you have 5 anyons, so that's F5.
Oh, okay.
Okay.
I see.
So if
I
you
see.
have
Okay.
10, so it's in general Fn, where F is the Fibonacci number.
Okay. Okay.
You can calculate it this way.
Actually, you mentioned creation or destruction during the calculation. I think that's predicated on only the creation being at the beginning, and rather than actually during the calculation. Is that even an option? It would be a completely different Hilbert space, and I guess probably an infinite one.
So for the complete calculus, I need an infinite Hilbert space, because my terms can grow infinitely.
But even if you sort of constrained the total
so
number of
Fock spaces.
anyons at any one time, but allowed the creation and destruction of anyons, then it would presumably still be infinite.
Yeah,
So
yeah.
that was,
Because I mean,
Yes.
for verification purposes, you can't really deal with like infinite Hilbert space. That would
Infinite dimension.
yeah, of course. I mean,
But you needed
Wow.
For verification, you said.
Yeah.
Mm-hmm.
So I mean, you want to create a state space, but yeah.
I think you need all these techniques for abstracting the state space.
Yeah, of course.
And then there's cantilever first and non-cantilever Hilbert spaces.
By the way, actually in mathematics, Hilbert space was originally defined as infinite dimensional. So when
Yeah.
it is finite dimensional, it's called
Sure.
unitary space.
Mhm.
So I don't know why they call it Hilbert spaces. So actually correct mathematics definition that all the axioms of Hilbert space, one of them is infinite dimensional. But of course that's now not a common jargon for
I mean,
some reason.
for physical purposes, I think you need the finite to work with the finite systems.
You
So
can
you-
have a finite dimensional projection of the system, so which is infinite dimensional, but then you can have a reduction in some subspace which is finite dimensional. And actually, what we're talking about, you need the infinite degrees of freedom, for example. But like, for example, spin, rotations, you have infinite number of
You think in 3 dimensions.
Mm.
3 or any dimension. If you have rotation in 2 dimensions, infinite number. There's a continuum of rotation. Angles.
Well, yeah.
Okay, I think maybe we can stop and then coffee and then we can discuss. Yeah.
Good idea.
Thanks a lot. Thank you.
Yeah, it's still very, very, very
Good topic to discuss. To say, but actually.